Hi, my name is Alberto de la Torre, and I'll be your host and moderator today. Thank you for joining us for this long-range colloquium organized by the Virtual Science Forum. If this is your first time joining us, I will put some information about how you can join our efforts in the chat. And not in question and answers, please use the raise hand option in the participant panel, which you can find at the bottom of your screens. I will be moderating the participants' discussion, so I will let the speaker know that there's a question from the audience and unmute you to ask your question live. So let's move to our colloquium today, which will be presented by someone I have the pleasure to consider a very close friend, Michael Sentef. Michael is an Aminuder group leader at the Max Planck Institute for the Structure and Dynamics of Matter in Hamburg. He's a leader in the field of ultrafast light-matter interactions in quantum materials, with many of the overarching concepts he has explored being highlighted in a recent review article, which I think he's going to be mentioning today. And in this talk, Michael will introduce and discuss the advantages of a new approach for light matter-based engineering on quantum materials. So without further ado, Michael, whenever you're ready.
Thanks a lot, Alberto, for the kind introduction. And it's great to see so many friends in the audience here today. And also my newly acquainted friends from the Virtual Science Forum, which I had the pleasure to join recently. With so far very modest contributions from my side, but I hope that there will be more to come in the near future. I think it's a great idea, and thanks very much for starting this whole endeavor, and also for, of course, inviting me today to give this very nice long-range colloquium. So let me first start the screen sharing. Can you see this? Great. Okay, now I need to figure out how to remove the video of the other panelists. Okay, great. So today I'm gonna talk about cavity quantum materials, which I've started working on basically back in 2017 or so, after joining the Max Planck Institute in Hamburg as an Eminota group leader. And I got influenced there by the likes of Angel Rubio, who's the theory director there, and he's been working on cavity chemistry and related topics for a longer time already. So I really got inspired by these efforts, and it was kind of a natural extension from my work, earlier work on non-equilibrium dynamics and ultrafast light matter interactions in pump probe experiments. But then actually, when I submitted the abstract, I wanted to talk about cavity quantum materials because I think it's a very nice topic. And the papers, the references that I'm going to discuss today are here on the left. So one is this review article that we wrote together that Alberto already introduced briefly. Then I'm going to talk about cavity control of the Hubbard model and light matter coupling and quantum geometry in moiré materials, which is a more recent work which we have put on archive and submitted for publication. But then I realized that actually I also wanted to show some more recent results, unpublished ones by my group members. So you will see them interspersed in between these references. And I will try to squeeze in more or less 6 papers in the roughly 45 minutes or so of speaking time. But importantly, please interrupt me anytime. I don't have to get through with my talk or anything like that. And we should have a discussion during the talk. Okay, so first of all, some coordinates. So we are in Hamburg in this building that you see here on the left, the Center for Free Electron Laser Science, which the Max Planck Institute for the Structure and Dynamics of Matter is located in. Then we're expanding, so there's this new building here on the right-hand side. So we're still growing, the institute is still quite young. And then there's also an ongoing collaboration with the Center for Computational Quantum Physics of the Simons Foundation in New York. And more formally, this has been established now through this Max Planck New York Center for Non-Equilibrium Quantum Phenomena. And I should also advertise that we have this International Max Planck Research School, IMPRS UFAST, which I will also advertise again at the very end. And we have opportunities for PhD students in the future. All right. So for a proper colloquium, I want to start on the, in the bigger picture. and think about non-equilibrium and light-matter interaction in a more general framework. And we all know that, we live on this planet right here, this beautiful one, and there's the sun shining most of the days, not always in Hamburg, but at least right now the weather is quite nice. And importantly, the important feature of all of this is the non-equilibrium is important to even enable life. And this was realized, for example, by Erwin Schrödinger in his essay, What is Life?, which he published in the 40s, in which he discussed how we are basically entropy creation machines. Every living being is. So we basically are a driven dissipative system that is in some kind of more or less steady state. And this is how life comes about. So it's very natural actually to think about non-equilibrium in nature. It's actually much more natural in a sense than to think about ground states. And of course, light-matter interactions are also of key importance, not only directly through this process by which the sun gives us the energy through the photons, but also, for example, for processes such as photosynthesis, in which chemical reactions are triggered that allow us to have plants that we can then eat and digest and get rid of the entropy again in order to not die the death of entropy. And also, light-matter interactions are, of course, of key importance for the stability of matter. If you think about atoms, the Coulomb interactions in the atoms are mediated by virtual photon exchange, and the coupling strength between light and matter, which is given by the fine structure constant, is of key importance to enable the stability of matter in the first place. So all of that taking together, it's very natural to ask, can we also imply non-equilibrium, and can we employ light-matter interactions to modify materials' properties? And at first glance, you might say no, because when you look up the fine structure constant, which gives you the strength of interactions between photons and charged particles, then you find that it's, of course, given by the famous fine structure constant. And as the name already says, it's a constant, as far as we know. So it's given by a lot of constants of nature. And being constant, it is good, because that means that atoms don't just fall apart because of some random fluctuations of the strength of the fine structure constants. That would be terrible. But on the other hand, it also seems to imply that there's a restriction of the tunability of this important coupling constant. However, now we know that this is not necessarily the case, and this is the topic of my talk. The topic of my talk is basically how we can explore this phase diagram, or this phase space that I'm drawing here, which is spanned by, on the one axis, the strength of the light-matter coupling, which I call G, and on the other hand, the non-equilibriumness, or the excitation of matter by driving with a laser, or with photons more generally. So here I'm drawing the y-axis, which is given by the photon number, or the driving strength of the laser in some general sense. And really, when you think about it, all of the exciting many-body ground states in quantum materials, condensed matter, and so forth, that many of us are excited about, we only live here in this lower left corner of this phase space. And in the vacuum, the G is basically given by alpha. And already here, of course, you know that you have a lot of tunability by changing, for example, the chemistry, stoichiometry, and so forth, applying pressure, changing temperature. You have all of these exciting phase diagrams, but those are not the topic of my talk. Instead, I want to explore what happens if, on the one hand, we drive a material with a strong laser, and discuss a few ideas related to non-thermality in quantum materials, as well as Floquet engineering. And then in this sort of second part of my talk, give you a natural crossover between this limit of, let's say, rather small light-matter coupling, but a strongly driven systems on the one hand, and cavity quantum materials, which is quantum materials interacting with strongly with with dark modes in a cavity in some limit. And in particular, I want to advertise that, of course, there's a lot of plenty of room at the bottom, or plenty of room in this phase space. And this is what I want to discuss in terms of the classical to quantum crossover. So here we have strong laser fields, which can be to some good approximation usually described by just classical electromagnetism and the Maxwell equation. And here we're in a limit where we have to treat the dynamical quantum degrees of freedom of the photons explicitly. And there's of course a whole range of phase space to be discovered, as I said. Okay, so this is the scope of my talk. And of course, there has been a lot of activity already experimentally that I want to acknowledge on the optical control or ultrafast control of driven quantum materials. So this is a slide that Matteo nicely provided. So it shows a laser pulse impinging on some interesting material. And I'm just going to show a few or mention a few of the interesting results that have been obtained. For example, it has been shown that a material can be driven into a hidden phase, which is not straightforwardly thermally accessible by equilibrium means. Photo-induced phase transitions, of course, have been a big topic. More recently, also the so-called band structure engineering by periodically driving a band structure in the material. It has been shown that one can get these so-called Floquet engineering effects, most notably here in the group of Nugetic at MIT. Then, of course, light-induced superconductivity, where I should have put an asterisk here because we should call it light-induced superconducting-like responses in the time domain. Matteo is one of the pioneers here in the lab of Andrea Cavalieri in Hamburg. Then, for example, ferroelectric switching, Tobia is also in the audience, one of the pioneers in this field. And also, of course, ultrafast magnetism, which was already started in the 90s. So all of this is great. And in fact, we've decided to review the field and write a perspective on the field in this colloquium article that I mentioned before, with this group of people shown here at the bottom. And the abstract is shown up here. So we review recent progress in utilizing ultrafast light-matter interaction to control the macroscopic properties of quantum materials, and particularly emphasize photo-induced phenomena that do not result from just ultrafast heating, but rather emerge from microscopic processes that are inherently non-thermal in nature. So this non-thermality aspect is kind of important. And many of these processes can be described as transient modifications of the free energy landscape in the time domain. For example, triggered by a redistribution of quasi-particle populations, dynamical modification of coupling strengths, or the resonant driving of the crystal lattice. And other pathways then result from the coherent dressing of a material's quantum states by the light field. This is what we now call Floquet engineering. And then we basically give a tour de force through the techniques that are used to probe these states in the time domain with various kind of spectroscopies, transport, scattering techniques, and so forth. If you want to learn more about all of these exciting developments, please read our paper and the references therein. But now I'm going to focus specifically on one aspect and show you some recent results, namely so here I'm giving just an overview of different interesting physical processes that can be triggered by a short laser excitation of a system. So for example, it can be used to probe the coherent oscillations of collective modes, such as coherent phonons, but also more exotic modes, such as the Higgs mode in superconductors. This is one application of using time domain techniques. Basically, you hit the system and you excite some collective modes and you see some oscillations in some spectroscopy or scattering as mentioned. And therefore, this allows you to access collective modes that might be harder to probe in the frequency domain in a classical, static spectroscopy type of way, or dynamical in the sense of frequency dependence, but static in the sense of doing linear response. So here you're not restricted to linear response. You can hit the system as hard as you want, and you can, for example, also see how the modes get changed eventually when you drive the system far away from equilibrium. This is shown in panel D, where you can explore nonlinearities, so non-harmonic parts of this effective free energy landscape. And this gives rise to a lot of interesting phenomena. Then I mentioned the ultrafast switching between two ground states that are degenerate, but also, for example, into some hidden non-thermal hidden state or metastable state shown here. And finally, the criticality in which we really change dynamically in the effective free energy landscape of the material and drive the material through a phase transition and probe critical dynamics. And this brings me to the first project that I want to show here, the paper by Mona, who's also in the audience, namely dynamical phase transitions in quantum magnets. Okay, so here is a motivation by our host, Alberto, yet unpublished data, beautiful data on an optically pumped iridate material, which is a mod insulator with some magnetic ordering. And what is shown here in this sketch is basically how by optically pumping this iridate material, one can induce a non-thermal population of magnons shown down here. So here is the n of omega as the occupation of magnons as a function of the Magnon frequency. And at equilibrium, you have a Bose-Einstein distribution of thermally populated magnons. But then by the time that the laser is hitting the material, you can see that in this cartoon that you can get some non-thermal populations. You get a hump here, you get some optically excited magnons, then they thermalize within the Magnon subsystem to some higher effective temperature and eventually cool down by coupling to the substrate and other degrees of freedom, such as phonons. And the interesting finding of the study was that there's a separation of phase transitions in this material, depicted here by these effective free energy landscapes up here. So there's a phase at low fluence, F is the laser fluence or the excitation strength, at which there is still a finite autoparameter of the material, which then at some critical fluence goes away and you don't see an autoparameter anymore. But still there's at a yet higher fluence, one observes a critical slowing down when at equilibrium you would expect nothing interesting, because basically here the long range order has been gone, but still there's some other phase boundary in this non-equilibrium phase diagram, shown also here on the right hand side. So there's this critical fluence FC, but then there's this other fluence F star, up to which you can drive the system and find a divergent timescale in the recovery dynamics of this magnetic ordering. This is, of course, very interesting because basically it means that by going out of equilibrium and away from thermality, you can split an equilibrium phase transition into two parts and see interesting new critical behavior. And I think there is a question in the audience.
Yeah, if I could. So the intermediate regime, you still show a slightly bistable free energy landscape. So does that suggest that there's 2-point correlation functions which are non-trivial in that zero VEV region?
I guess Alberto should answer the question.
It's a good question. It's something that I haven't thought about, so maybe we can talk afterwards and we can let Michael continue.
Yeah,
sure. Yeah, thanks for the question. Anyway, so then there was a theory paper stimulated in part by experiments like this, in which it was shown that by driving a 2D Hubbard model in the strongly correlated anti-ferromagnetically ordered phase, it was shown that there is a critical behavior, so there's a critical fluence, if you wish, at which the system becomes thermal, but with an effective temperature that is higher than the equilibrium one, which I think here was the calculation was started at 0 temperature, and below which you find a subthermal distribution of spin waves, meaning that this does not follow a Bose-Einstein distribution, but instead the n of omega goes to a finite value as omega goes to 0. It diverges as 1 over omega at the critical point, and then it diverges faster than 1 over omega, implying a superthermal population of magnons above the critical strength of the field or fluence. But I should mention that in this paper, it was a basically non-interacting Magnon theory that was applied here. And you might ask the question, of course, if you see these non-thermal states, what happens if you add Magnon-Magnon interactions to the story? And naively, you would expect that scattering between magnons would thermalize the Magnon system. And this is exactly where our calculation and our project comes in. So we start from a 2D Heisenberg antiferromagnet. I'm writing here XXC, but see the anisotropy is delta is 1, so it's really the isotropic Heisenberg model. And then we use spin wave theory, standard spin wave theory, to get a bilinear Magnon Hamiltonian as usual, and Magnon-Magnon interactions by this Holstein-Primakov transformation. And the first step that we did is basically now we have a term that we can switch on and off, and we can reproduce the theory that was published before, or we can look at the theory in the presence of Magnon-Magnon interactions. In the absence of Magnon-Magnon interactions, what we did is we wrote down a nonlinear kinetic equations for non-interacting magnons. So basically one equation for each frequency separately, which has a G in, which is a scattering in term producing magnons, gamma out, which is a coupling to a substrate, removing magnons from the system, and importantly, this nonlinearity which allows us to tune the system such that it reproduces the behavior seen in the previous paper. So essentially what you find is if you solve this equation for the steady state, which is very simple, you just set the equation equal to 0 and solve for n, you find, because it's nonlinear, you find two solutions. One of them is, of course, unphysical because it has negative occupations, but the physical solution of this equation gives you exactly the behavior that I was showing before, namely this subthermal population for G lesser than 1, this effective thermal state at G equal to 1, and for G greater than 1, faster than 1 over omega divergence of the Magnon occupation. Okay, so this is our starting point. This is the non-interacting theory. And then what we did, we added interactions on the level of the semi-classical Boltzmann equation. So we calculated diagrams like this and basically supplanted this kinetic equation by a scattering term from the Boltzmann equation. And what we found, and this is the first figure of the paper, going to be submitted next week, I hope, is when we plot now omega times, this is now omega times n of omega as a function of the frequency, we see that there's at G equal to 1, there's this critical behavior as before. So it, now omega times n goes to a finite value, meaning that we reproduce this 1 over omega divergence in the occupation itself, as we should. And now if you look here for a value of the control parameter G less than 1, there's hardly any difference between the non-interacting theory, which is the straight line here, and the data points, which is the interacting theory. So Magnon-Magnon scattering doesn't do much in this subthermal regime of the non-equilibrium phase diagram. But importantly, if we go above the critical point, G greater than 1, we do find a rearrangement of magnons. So the solid line here again is the non-interacting result, and you see here that basically the scattering tries to thermalize magnons. So it tries to flatten out this thing and bring it towards the thermal result. However, at the cost of a stronger divergence at the lowest frequency, and you see this better in the inset here. you really see the stronger than non-interacting divergence. And this is, of course, very interesting. We asked ourselves, so how does this fit into our picture of the system trying to thermalize under Magnon scattering? And when we looked at this more closely, we did find that, in fact, this is, I should say, a finite size calculation. So we always have to take a finite momentum grid in order to solve the Boltzmann equation, which corresponds to a finite lattice in real space with periodic boundary conditions. And when Mona did a more careful analysis of finite size scaling of these results, we found that actually what this stronger than 1 over omega squared divergence of n is trying to do is to form a delta function at zero frequency, a delta function peak at zero frequency in the thermodynamic limit. So we have a thermal distribution of Magnons plus a singular contribution from the zero frequency Magnons. So this is very interesting, and actually it can be understood in this non-equilibrium phase diagram that I'm drawing down here. When I'm plotting the number of Magnons in the system as a function of the energy, then if we are restricting ourselves only to thermal states, then we fall onto this line that is shown here. So this is basically, if you change temperature, then you know that in the usual ensemble, you just I give you the temperature and you know the energy and the Magnon number and everything's fixed, right? But now if we allow ourselves to go away from the thermal line, then this is what really happens in our theory. So in the subthermal regime, G lesser than 1, we actually go below the thermal line. So we have fewer Magnons per energy than in the thermal state. At the critical point, we cross the thermal line. This is exactly the thermal state at criticality. And then above the critical point, we are in this superthermal, or in the thermodynamic limit, thermal plus delta function regime, where we have too many Magnons to accommodate for a given energy. And what the system does is it basically pushes all of these excess Magnons into the delta function peak at zero frequency. And now the curious thing that we found is that now, of course, you might say, well, this is a bit trivial because already the non-interacting equation of kinetic equation already shows similar features. If you follow the orange data points, this is the non-interacting steady state that we start with. And the green data points here are the ones that the system flows to when we include the Magnon scattering and let it evolve under the drive plus dissipation into the bath plus the Magnon scattering. And the interesting feature that you realize is that, in fact, the interactions do not try to push the system closer to the thermal line, but actually further away. And this is very interesting. And what you moreover see is that, in fact, if you plot this Magnon number now as a function of the G parameter, so these are all different values of G, so you can plot them in a different way and take a derivative, the dN by dG, shown here now for different system sizes from 80 by 100 to 120 linear dimensions. So the largest one is 120 by 120 lattice. Then you see that the system tries to develop a singularity in dN by dG. Shown here, the singularity moves closer to the expected critical point at G equal to 1, and the inset shows actually scaling behavior, that all of these curves collapse onto a single curve when scaled in the right way. So the distance from criticality times the linear system size on the x-axis and dN by dG divided by the square root of L on the y-axis here for this static observable. And what's more is when we looked at the decay rate of the system as it goes from the non-interacting to the interacting state, or if you start in the steady state of the full Hamiltonian and put some perturbation in and let it relax back, then you can extract decay rates. And there's a universal decay rate in all of the quantities, in all of the observables that we checked. And this decay rate, plotted again as a function of this control parameter G, also shows a singular behavior, and in fact, a critical slowing down, or at least behavior consistent with a critical slowing down, I should say, in the thermodynamic limit. And again, the scaling behavior. So basically, if you trace these different curves for 80, 100, 120, if you go towards the thermodynamic limit, you will see that this decay rate tries to go to 0, meaning that the time scale tries to diverge. So we find static and dynamic criticality in the interacting system at this critical point. And now when you think more about it, then you can draw a non-equilibrium phase diagram, in which I'm now plotting the inverse spin length 1 over s of the Heisenberg Hamiltonian on the y-axis, and the control parameter of our drive g. So g here is the ratio. I should have mentioned this. G is the ratio of the in scattering divided by gamma out, the scattering into the substrate. So it's a measure of the strength of the drive at a fixed dissipation to the substrate. And what we see basically in this phase diagram here is here's the ordered state at 0 temperature. There's mathematically, you can define a smallest spin length at which you still get ordered state at 0 temperature in 2D. And then there's this ordered subthermal state. Basically, this black line corresponds to the line of vanishing ordered magnetic moment as we crank up the G. And then there's this disordered subthermal state. Here's the thermal line. So this is the critical point, which is invariant under Magnon scattering. So G equal to 1 is universally, it's a thermal state, so there's nothing to thermalize for the Magnon scattering. And then there's this disordered superthermal state with the delta function in the thermodynamic limit and the critical endpoint. And we are now trying to characterize this a bit more and understand it a bit better, but I think this is a very nice and interesting result. And Babak has a question.
Yeah, I was trying to understand the low G limit of this phase diagram. Are you saying that everything is subthermal when even for small G?
I'm saying that well, if G is 0, then everything's thermal, right? Here we're in the ground. Here we're in the ground state.
Right. Now
that the G is we have the subthermal regime. I should have pointed out that G is the ratio of the in scattering divided by the out scattering. So if you only so you have to have this drive plus dissipation, then you have this ordered subthermal regime. But does that make sense?
That's how it is.
Say it again.
That's true for any non-zero G.
That's true for any non-zero G. That's just basically this is just what came out of the study of the non-interacting theory by Niklas Waldorf et al. You should look at the Fisser FB that I mentioned before. You can find this. This is, of course, by itself an interesting result. Actually, it means that you can avoid, in some sense, the Mermin-Wagner theorem if you apply the right drive and dissipation. Of course, now you can argue whether how this depends on the coupling to the substrate and the type of dissipation that you have in the system. So, so I should have pointed this out.
Okay, thanks.
Sure. All right. Good. So this is the first paper that I wanted to highlight. Then I want to briefly mention more recent results by my other student, Damian, in collaboration with the Nijmegen group of Johan Menting and Giuseppe Carleo about the dynamics of these 2D quantum magnets with neural quantum states, which is a rather new a topic, of course, a very hot topic in the community right now, trying to simulate quantum many-body Hamiltonians with this variational ansatz inspired by neural networks. And here I just want to go over this rather quickly, but point out that, for example, we can actually simulate quite stable dynamics in square lattice Heisenberg models, similar to the ones that Mona was looking at with the different method. And this was already found by Fabiani and Menting in an earlier work. And actually, if we tried to look at a ladder, the Heisenberg ladder, in order to benchmark this new method and the dynamics with this method against, for example, MPS calculations or TensorNet calculations, but found it countered these numerical instabilities that are indicated down here. So if you drive the system with a short pulse, then at some point, if you drive it too much, then the energy runs away and the dynamics becomes unstable. And this has been plaguing us for a while now. But we think, and in fact, this has been seen also in studies of other Hamiltonians. But now we think that we've discovered a way to diagnose where these instabilities come from, namely by looking at the machine learning inspired validation error, which is a way of looking at Monte Carlo samples from separate samples and do this validation error diagnosis between two different Monte Carlo sets. If you want to learn more about this, then I encourage you to look at slides that we have on the website by Damian. And I think I also encourage Damian to give a talk in the Virtual Science Forum Speakers Corner as soon as we have put this on archive. And I also want to highlight or mention that there will be a long-range colloquium in May given by Giuseppe Carleo, who is the pioneer of this field and has published this very nice netcat code. And I guess Giuseppe will talk more about machine learning in the physical sciences in his colloquium. All right, this is just an advertisement. So now let me come to the second part of my talk, and just wondering whether I will even manage to get to the cavity part. Let's see. So Floquet engineering of quantum materials. So far, I should maybe recap for a second. So far, I've been talking about engineering non-thermal populations of some excitations like magnons in a system, and asked the question, can you induce critical behavior by doing that? And the topic of Floquet engineering is a bit different. In Floquet engineering, typically we ask the question, can we induce new states and create effective Hamiltonians, irrespective of the populations of these energy states, by driving materials with lasers. And this is, for example, illustrated here on the left-hand side by having a honeycomb lattice model with some nearest neighbor hopping T0. And in the optically dressed state, one can envision, or I can show that, for example, one can renormalize this nearest neighbor hopping, but one can also induce other hopping terms in the Hamiltonian, which may be absent even in equilibrium. And this has led to a range of interesting avenues for research. So one is, for example, band structure engineering, inducing Floquet sidebands and changing the effective band structure of materials, breaking certain symmetries and inducing non-trivial topological invariants starting from trivial topology is one interesting topic as well. Excitons, magnetism, you name it, the fractional quantum Hall effect was proposed as a Floquet engineered state of matter, and also superconductivity. This is just, of course, a laundry list. And I want to specifically focus in what follows on the Floquet engineering of spin exchange in a strongly correlated Hamiltonian. And this was pioneered by Martin Eckstein's group in this nice paper in 2015, led by actually the same Johan Menting that I acknowledged before in a collaboration on the NQS. And it was shown here in this paper that by driving a Hubbard model, and one could basically change the virtual intermediate states in a spin exchange process. So if you think about two spins on two sides and you drive now with a laser by, you give the system the chance to interact with the photon degrees of freedom, you can absorb or emit photons in the transition between the spin exchange process between this state and the reversed spin state, going through this intermediate doubly occupied state, and basically change the energy cost of this intermediate state by the emission or absorption of n photons, u plus minus n times the photon frequency here. And it was shown in this paper that you can, in this way, by the photon dressing of these intermediate states, modify the kinetic exchange interaction. One can, for example, suppress it, driving with a frequency that is larger than the Hubbard U, or one can even enhance it a little bit by driving with a frequency that is smaller or red-detuned from the Hubbard U. As you can see, because this energy denominator changes sign as you go with omega through U. Yeah, so you see some interesting behavior. But of course, this has already inspired a number of interesting experiments. But there's a caveat to this. Usually, to see a healthy, measurable effect, you need strong lasers. And then you encounter problems with heating in the real world. You always heat your samples when you apply a strong laser intensities. And also, it's typically a short-lived effect. So all of this Floquet engineering relies on the fact that you apply a laser, and in the presence of the laser pulse, you have these dressing phenomena. But then, as the laser pulse is gone, basically the physics is back to the same Hamiltonian that governed the material before you applied the laser. So all of these are, very interesting. And I see a question again.
If I could quickly, so with this photon pumping, could you say just a little bit more about what you mean by modifying the kinetic exchange?
What I mean by modifying kinetic exchange, okay. What I mean specifically is basically, you think about it like this. You have a hopping that you dress by a electromagnetic field. And if you change, if you now apply this idea of Floquet engineering, basically you can renormalize the hopping. Think of it just by basically you have a periodically modulated phase in the hopping by some vector potential A of t. And now you integrate out. So basically you go to the high frequency limit, for example, then you can average over a cycle of the pulse, and you will see that you get a modification of the hopping by a Bessel function, which is the argument of which is the strength, the amplitude of the drive, of the periodic drive. And that way you can reduce the effective hopping in this high frequency limit. And now if you do that, then basically your kinetic exchange interaction J, I should have written this somewhere, is given by something like 4 times t squared, the hopping squared divided by u. And now if your hopping is smaller, then you've also effectively changed and reduced your kinetic exchange interaction. Does that make any sense?
Yeah, but the motivation for asking was whether or not you go beyond a sort of a Boltzmann paradigm for how you actually discern the rate of exchange. So I was thinking again in the non-equilibrium aspect.
Okay. So here, this paper specifically is talking about the Floquet engineering limit. So basically, you have this stressed band structure that you can then you can do the Floquet construction, which I'm not discussing here very much, but basically you modify you go to a quasi-static picture again, stroboscopic picture, where you've renormalized your Hamiltonian and then say, well, in some limit, the system wants to be in the ground state of that new Hamiltonian, and this is this limit of the pure Floquet engineering.
Thank you.
And then of course you're right. Then there are finite frequency corrections to that picture, absolutely, because this is not the only thing that will happen. But at the same time, as mentioned down here, you will also start heating up the system. The system will not be in the ground state of this new Hamiltonian anymore, but instead of in some excited state, right? And then, of course, you run into all of the trouble of trying to discern the effects of all of these different things, and they play together in a complicated, interesting system.
Thank you.
Right. But that's thanks for asking this excellent question, because this motivates already where I'm going. Because now the question is, can we also do this with the vacuum? So in the beginning, I showed that the stability of matter depends on the fine structure constant. And when you think about it, this is a property of the vacuum, right? The stability of an atom actually is a property not only of the atom, but also of the vacuum surrounding it, which provides the virtual photon modes that can be exchanged, give rise to the Coulomb interaction, and so forth. So in other words, changing the vacuum changes the matter. And the same question you can ask here. So if this is true for atoms, then why is it not true for materials? Because material, in the end of the day, is just 10 to the 23 atoms, right? So if you can do it with one atom, why not do it with 10 to the 23? And the answer that I want to give here is basically, yes, we can control the spin exchange also in the dark by applying or by putting the system in a cavity or in some polaritonic or plasmonic surrounding. And what we have to do is we have to replace the strong fields by strong light matter coupling. So if you remember the phase diagram that I showed in the beginning, I had this one axis, which was the number of photons in the system, and the other axis, which was the strength of the light matter coupling. And now if we have a control knob to tune the strength of the coupling, then we can actually also modify the relevant effective interactions that govern the low energy physics of the material. And in order to illustrate that, we now come to the cavity quantum materials, or what I call here QED quantum materials, quantum electrodynamical quantum materials. I just realized it has the double quantum, so it's even better for writing grant applications these days because everything is now quantum, right? And let's talk about strong light matter coupling. So this is actually inspired and pioneered, as I also mentioned earlier in my talk, by the field of polaritonic chemistry. The key idea of this field is really in some sense, very simple. Namely, exactly the thing that I mentioned before is that if you can tune the effective light matter coupling strength, then not only is the stability of a single atom changed, and you can, for example, you can also change the bond length of a molecule, or even affect a chemical reaction, because a chemical reaction at the end of the day is nothing but the valence electrons being exchanged between two molecules and then forming a new compound, right? So it's kind of natural to expect that this is possible, but of course it's still quite an achievement to actually demonstrate that, because you need to achieve this regime of strong light matter coupling. So you need to change your coupling strength by quite a bit. But this is pioneered by people like Thomas Ebbesen in Strasbourg, and then there has been a flurry of recent nice review articles, each of which I can recommend reading about this topic. But now the question is, of course, a quantum material is a huge molecule, and this should actually be very good for this idea of strong light matter coupling, because, for example, in this chemistry framework, it's very good if you have a lot of separate emitters, or a lot of separate molecules or atoms interact with the same cavity mode, and that leads to the phenomenon of so-called collective strong light matter coupling. So quantum materials are naturally a collection of many emitters. One interesting idea in this direction was, well, if you can control the electron boson coupling, for example, electron phonon coupling in a conventional superconductor, you could also change superconductivity. And this was proposed by us a few years ago in this paper, in which we looked specifically at a material. It's not so important here which material that was, but we specifically looked at the coupling between a photon mode in a cavity and a phonon mode in the material. And the phonon mode in turn is important for the electronic properties of that material. And therefore, it's quite natural to expect that if you change the phonon mode and you create a polariton mode, a hybrid mode of photon and phonon, you, for example, soften the mode or redistribute the coupling strength between the electrons and the phonon into the electrons, into the electron and the two polariton branches of the light cone of the light and the optical phonon in this case. Here we showed that this is actually expected to influence superconductivity. But more importantly, in a group of Thomas Ebbesen, it was recently, 1.5 years ago, I guess, this was put on archive, in which they showed that if you put a superconductor embedded into a polymer matrix onto a gold surface, at which you have these surface plasmon polaritons, which are hybrid particles of the electromagnetic field of the vacuum and the displacements of plasmons at the surface of gold. By doing this construction, they showed that actually one could change the superconducting critical temperature, or at least see a change in the onset temperature of the Meissner effect by quite a bit, so a quite substantial change. Now, of course, this paper is still not published, and of course, this is, as you can imagine, a horribly difficult experiment, and there are a lot of different possibilities of other interpretations of data and so forth. So I'm not saying that this is the final word on this story, but I think that it's been demonstrated pretty clearly that beyond chemistry, there's also the chance to change the properties of materials by the interaction with the vacuum of some electromagnetic field. Okay, and then I should acknowledge a lot of other works in the same realm. I guess Jonathan Curtis is in the audience. He also wrote a very nice paper on this. And our work now is not about superconductivity, but instead about the modification of the exchange coupling by not driving it with the material with a classical electromagnetic field, but instead putting it in a cavity and let it interact with the cavity mode of such a cavity, the cavity photon mode of such a cavity. Okay, and this is work published last year, nice collaboration with Jia-Jun Lee at University of Erlangen and in the group of Martin Eckstein. So let me briefly discuss that paper. So what we looked at was a Hubbard model in a cavity. So here we have just the usual hopping term or kinetic energy term of a Hubbard model, coupled now to a cavity mode with a bare frequency omega through this Pyle substitution in the dipole approximation, the long wavelength or Q equal to 0 limit of the photon mode, which is usually a good approximation, and supplanting it with Hubbard U term. And now this A term here is not the classical. In the classical limit, you would here just put the vector potential of the electromagnetic field of the laser. But in the quantum limit, you replace the A, as is known from quantum electrodynamics, by the coupling strength G times A plus A dagger of the bosonic field of these modes. And now you have a new Hamiltonian, which you can solve, and you can, in theory, of course, mathematically just tune the coupling strength to whatever you want and explore what happens. But the interesting thing that we found, going back to the earlier paper that I showed, the Menting paper in 2015 on the Floquet engineering with a classical field, we actually found in this work here that the quantum system crosses over into the Floquet limit if you take the photon number to infinity, keeping G times the square root of the photon number fixed. So in some sense, you have to scale, you have this double scaling limit. I don't know if that's the right term, but you have to scale at the same time the number of photons to infinity, but the coupling strength basically to 0, keeping this ratio fixed. And in this limit, you get to the Floquet limit. So you have a large photon number, but a weak light matter coupling strength in the classical limit. But the interesting finding of the paper was that you don't even need a coherent state. So classically, you would expect from a laser, you have a coherent state of photons. But in order to do Floquet engineering, you don't even need that. Yeah, you can also, it's good enough to use photon number states to see the same effects of Floquet engineering, the same change of the effective magnetic exchange coupling that I mentioned before. If the coupling strength G is sufficiently strong. And this is highlighted by this picture. So here I'm plotting the exchange coupling divided by the one without the cavity. So it starts at 1, and the A parameter is now basically G times the expectation value of A plus A dagger, either in some coherent state or some number state. Here I'm plotting number states. You see that at n equal to 0, really the vacuum of the photons, photon Fock space, this is very different. So n equal to 0 is very different, but already a single photon, one photon state is sufficient to basically reproduce the salient features of the Floquet engineering limit as you turn on the strength of the coupling, if you do the scaling in the correct way. And here I'm showing, for example, going from 1 to 10 photon states. Already at 10 photon states, you reproduce the dashed line, and the dashed line is the classical Floquet engineering limit that we knew. And this is again true for both the red and blue detuning of the cavity frequency with respect to the Hubbard U in this material. And so the question, can we control the spin exchange with cavities, can be answered yes, if we replace the strong field by a strong light matter coupling. Now, of course, this is of course the real challenge experimentally to achieve this limit. Yeah. Okay, how much time do I have left? Like 5 minutes?
5 minutes to the half hour. You can go a little bit longer if you need to.
I think I'm gonna not need much more. So let me briefly go over this part here. So this is a paper that we submitted in March, which now explores basically the question of so what happens if you explore light matter coupling with flat band materials, which are of course very interesting because you're expecting to see strong correlation effects and maybe be able to reach the strong coupling limit of a theory more easily if you quench the kinetic energy of a band. And of course, this is very prominent recently with these twisted moiré materials, which I'm not going to discuss in much detail. But the important, the key message of our paper is that if you have a trivial quantum geometry, that is a flat band which does not have any interesting quantum geometry, but it's just localized because you basically have decoupled sites in the model, for example, just like an atomic insulator. Here, there's, as expected, there's no light matter coupling because the band velocity and the band curvature are both zero, and you would expect naively, classically, so to speak, that the light matter coupling is, minimal coupling is p minus a time squared, and if the paramagnetic coupling is the current times the vector potential, or the velocity times the vector potential, and if the velocity is zero, then this term is zero, and the same holds true for the diamagnetic term. If the band curvature is zero, then the effective mass is infinite, and therefore there's no diamagnetic a squared divided by the mass coupling because the mass is infinite. However, in the presence of a non-trivial quantum geometry, this is not true. And this is the key result of the paper here, that besides the linear term, which really vanishes for a flat band, it's just given by the derivative of the band dispersion along the direction of the field. There's a quadratic intraband term, a diamagnetic term, which not only has the usual second derivative of the dispersion, but also a term which is related to the quantum geometry of the band. And then we looked at a toy model to illustrate this, and also at graphene, at twisted bilayer graphene. Along the same token, I also want to highlight that there's this linear interband coupling, which we know as dipole matrix elements. And these dipole matrix elements are in fact related to the interband Berry connection. And in some limit, this goes then back to what is known. For example, if you have a two-band system, then you know that everything's given by the Berry curvature and angular momentum conservation for an optical transition. But this equation is more general, and especially for more than two-band systems, this becomes very interesting because you can really probe, in some sense, the interband Berry connection and quantum geometry of different pairs of bands by looking at the optical transitions. And I would also like to highlight this recent paper here in the group of Ashwin Vishwanath by Junyoung Ahn at Harvard, in which they showed similar effects of the quantum geometry, not on the light matter coupling itself, but on all kinds of interesting nonlinear optical responses. So I recommend also looking at this paper. And okay, so this is the story. And to finally also show unpublished recent result by these gentlemen here, Christian Eckhardt, who's in the audience, Giacomo Mustafa, in collaboration with the group of Dante Kennis, and also Christoph Karasch. We look at a rather simple, exactly solvable model for a quantum chain in a cavity, namely just the non-interacting limit of the Hubbard model in a cavity that I was showing before. So basically, we just have a hopping term dressed by this Piolt substitution with the coupling to the electromagnetic field as before, and the mode of the cavity, the mode frequency of the cavity, this harmonic oscillator part here. And by realizing that one can write this as some coupling times the kinetic energy plus some other coupling times the current of the system, we could actually show that one can solve this exactly. And for example, look at the photon wave function in the coupled system and show that this is a squeezed state, and the squeezing then of the state depends on the coupling strength and also on the frequency with respect to the tuning of the photon frequency with respect to the kinetic energy of the electrons. And finally, the electronic spectral function plotted down here. This is A of k and omega for different momenta. This, you see the cosine-like band dispersing around here. Then we see these shake-off states, and we see the crossover of these shake-off peaks in the ARPIS signal, or the calculated ARPIS-like signal And for example, the renormalization of the effective mode frequency by the coupling to the electronic system. And we also recover the Floquet limit when we go to large photon numbers at weak coupling, similar to this scaling limit that I discussed before. So this is also upcoming. So finally, this is my summary. I'm just gonna leave this slide on. And I'm also getting interrupted by my 4-year-old who's trying to join the talk. So let me just leave the summary slide here, and more importantly, acknowledge all the wonderful people that have done this work with me together. These are all the collaborators of the projects that I showed. This is my group, I guess, before the pandemic. And this is the larger theory department with lots of inspiring collaborations as well. And let me finally, in the final minute or so, take the opportunity to again advertise that our group is open for new PhD students. The next call, for example, in this International Max Planck Research School is going to open probably in September. The deadline will be at the end of the year. So get in touch anytime if you're interested in joining us. Also for postdocs, there are opportunities. Just flashing or showing here a list of potential topics that could be your PhD topic. And finally, thank you for your kind attention.
Thank you, Michael, for a beautiful talk. Let me open the floor for questions. So you can ask questions by using the raise hand tool in the participant. Well, I can start with the question, Michael. These examples that you showed of light matter interactions in cavities, does this consider at all the polarization of that mode? Like, I know there are some ideas of using.
Yeah, it does. Yeah. What I didn't say, of course, in this talk is that you always have different mode polarizations, right? You have different modes in a cavity depending on the geometry. In another paper, for example, we looked at what happens if you have a circular depolarized mode in a cavity, and you have some means of choosing a right-handed circular depolarized mode over the left-handed counterpart. And by this, you break time reversal, and then you can induce a cavity Chern insulator. So that was one work. So yeah, definitely there's more to the story. Here I really focused only on one aspect, of course, yeah.
Jonathan, go ahead, please.
Yeah, thanks for the great talk. I had been wondering, it seems like in these, if you classically couple the electromagnetic field via the chiral substitution, my naive expectation is that you actually don't see much coupling, at least to lowest order, because it requires kind of the electron to fully traverse a closed loop in order to couple to the flux of the field, and this only arises at least cubic order in perturbation theory if you have longer range hoppings. But obviously, I guess that's not what you see when you do the Floquet or the quantum, like the full non-perturbative calculation. I was just wondering if you can, like, sort of what is qualitatively, what is like the missing ingredient in order to get this coupling, to sort of appear.
I'm not sure I fully understand your question, to be honest. Maybe it's easier to discuss this, offline or separately, so that I have time to. I'm just not entirely sure what you're asking, but
I mean, like, if you have
maybe you can rephrase the question.
Case. Yeah, if you have like the simplest possible system is, a dimer for the Hubbard model, then when an electron virtually hops and then hops back, it acquires exactly the opposite phase as it acquired on the first step. So the perturbative sort of coupling seems to vanish by that argument, at least in like the quasi-static limit.
So maybe the problem is that you're thinking about it in a static limit.
Yeah, I'm just wondering what exactly is required, like what exactly about the dynamics changes that argument. Maybe it's kind of too technical, but.
Yeah, I'm not sure I can answer that question off the top of my head, but I'm happy to discuss this more. I mean, you should look at the paper with Martin Eckstein's group, because there is this cavity Schrieffer-Wolff transformation, I think, which is very cool. It's also a technical answer, right? Yeah, look at the math. But I'm happy to think more about it in terms of intuitive physical arguments. Yeah.
Okay, thanks.
Thanks, Jonathan.
Go ahead, Tobias.
Yeah, hi. I have two questions. One is quite general and one is a bit detailed. The first one is, especially in the last experiment, did you consider the interaction with one mode of the cavity or multiple modes of the cavity? Because, you know, experimentally getting a single mode cavity, it's close to impossible, at least with these quantum materials. What did you, sorry, you might have said it, but I missed it.
Which one are you asking about? You said experiment, but I didn't do an experiment.
Sorry, prediction about the Hubbard model and controlling the
Hubbard model. Yeah, that was a single, that was a single mode Q = 0 approximation, which might be too crude. Actually, you can achieve that in a split ring resonator, I was told. But it's not strictly at Q = 0. It has a finite Q, right? I mean, small but finite, which might be important for some things. Now in a normal, like in a planar cavity that I guess you're asking about, of course, that's an excellent question, because that's not true. So and then you have multiple modes, right? You have a whole momentum branch of photons, at least one for each polarization. And then of course you're not allowed to actually, you're strictly speaking not allowed to use the dipole approximation and only consider Q = 0, but you have to take into account the whole branch of modes, which is in general theoretically a much harder problem. So in this paper about the cavity superconductivity, we did the full glory thing, because that was easy, because it was a coupling between the photon and the phonon, which is bilinear, and then you can diagonalize everything and just calculate polaritons and put that into a Migdal-Ashberg machine. But for the coupling to electrons, that's indeed an excellent question and an open problem that we need to discuss. Very.
Second question.
Yeah, sure.
This is more general, as I said. How much coupling is enough? So, in the sense that if I consider the few experiments that are out there, so the Emergent group, so to say, the coupling they get is quite small, actually, in terms of relative to the resonance they are coupling to.
Right.
But they claim exceptional effects. So I was wondering, from your predictions, do you have an explanation on why it seems that in the experiment that the coupling doesn't need to be so big to do something to these quantum materials? Or do you expect that in future experiments one has to achieve this very large?
Yeah. Well, I guess it's always a question of energy scales, right? So I would say that if you're close enough to a phase transition, or you already have an instability, then it might be enough to just push the system over by a tiny change, you know. Whereas, of course, if you want to achieve something from scratch, so you want to induce superconductivity in a material that's not superconducting anywhere in the phase diagram, then I would expect that you need a pretty strong coupling to do that. So does that help? I mean, I guess, for example, for the experiment of Ebison and the superconductor, well, first of all, I have to say that this is still so poorly understood that everything that I'm now saying comes with a disclaimer. But my feeling is that really what they're doing is they have a phonon-mediated superconductor. Then they put this in the cavity. They make the cavity resonant, or this plasmonic surface. They make it resonant with the phonon in the polymer, which acts as a transducer to couple the plasmons to the phonons in the superconductor. That's a multi-step process.
I was more referring to, for example, from the same group, they have this paper where they change the reactivity of molecules. Right? The
reactivity question, yeah. That's a different beast. That's a different beast, because there they have this collective strong coupling, right? So you have a weak coupling of each individual molecule to the cavity, But then the Q equal to 0 mode, like the coherent superposition of all of the different excited states, they conspire to interact as a superposition with they act like a giant supermolecule, more or less, interacting with just this one mode in the cavity. And then basically you trade the coupling of each of the atoms, a little bit coupling with each of the atoms with the cavity mode for this one stronger coupling enhanced by square root of n of the number of emitters coupled to the same mode at the cost of having a lot of dark states that don't couple at all. I think this is kind of the deal that they're doing. But again, I have to say that I know too little about the details of the experiments to really comment more about this. So, but my feeling is that the coupling strength the collective coupling strength might not be so small. Do you agree, or?
Well, I mean, by judging to the polariton splitting, it's difficult to answer, right? Because the splitting is small compared to the frequency.
You mean the Rabi splitting is small compared to...
Rabi splitting, I mean, if you calculate, you're certainly not in the ultra strong coupling, which is usually
the
limit that I would imagine is necessary to achieve for what you predict.
I don't think, I'm not sure I agree on this. I mean, the ultra strong coupling limit is definitely the most interesting one right there. This is where light and matter become so strongly, the coupling strength becomes the largest energy scale. So it doesn't even make sense to talk about light and matter anymore, but the coupling strength is the dominant term in the Hamiltonian, right? This is a completely new limit and you expect totally new physics. But I think if you just want to tune the balance, so the detailed balance between a ground state and an excited state, or one chemical reaction pathway and the other, or enhance superconductivity or suppress superconductivity or do things like that, it might already be enough to not be in that ultra strong, or what is it now called, deep strong coupling? I'm forgetting, like there's all this terminology there.
When you exceed the resonance frequency, basically.
You exceed all of the other scales, yeah. I hope that it doesn't really answer the question, but at least...
it did. As you can see, I was expecting only the ultrasound coupling to be relevant, and apparently not. Thanks.
Right. But if I may comment on this, it's a kind of a similar story to the light-induced superconductivity, for example, right? If I give you any random material and you try to induce superconductivity, you fail. However, if I give you a superconductor that already tries to be a superconductor at some different doping or some lower temperature or whatever, then you pump it, then you can, induce the correlations at a higher temperature effectively, things like that. So there in the same sense, right? You're not turning clay into gold, but you're turning something that's almost gold into more gold. Right. Okay. Jonathan has another question.
Yeah, I was about to say.
I guess if I'm allowed to ask more questions. So one way that you can couple the cavities to the electrons is through minimal coupling, as you described, and is kind of very clear. But also you could in principle consider like the Zeeman coupling, which is magnetic dipole interaction and will not just appear from minimal coupling. So is there kind of typically it's neglected in most of these treatments. Is there some reason why, or is it kind of just expected to be weaker for these particular modes?
Generically, I can say yes. Thanks for the question. Generically, I can say that we thought about it, and the Zeeman coupling is just suppressed by 1 over the speed of light, more or less, right? The magnetic dipole interaction is weaker by some orders of magnitude compared to the electric dipole interactions, just generically if you couple to electrons. Now, of course, in some cases, if the charge degrees of freedom are frozen out, then you can still have this in the strong terahertz pulse. You can still have the coupling to the magnetic dipole interaction. And I think Tobias Kamfrath, for example, in Berlin has been doing some terahertz magnetism experiments where they think that this is the effect, right? Now so I don't know. I mean, I guess in the cavity, for example, you might also be able to find a limit or a system in which this type of interaction is the dominant one. But you have to make sure that the other interaction, which is usually much bigger, is just not relevant, because for example, the charge degrees of freedom are frozen out or things like that. So I think this is what you should think about if you want to have that. Does that make sense?
Yeah, I was mostly wondering because I mean, what you said makes sense for these far field radiation,
yes.
for laser,
but
most cavities are definitely not far field, and so it's not as obvious to me that what you just said is actually going to be the case.
That's an excellent point. Yeah, we should. I should think more about the effects of the near field, which is something that I think we're exploring. Some people in our department are exploring with some Maxwell Schrödinger simulations where they have like all of the near field structure also in the system, and they can look at that. Yeah. So I do agree that it's not as clear in the near field.
Yeah.
Far field. So maybe, for example, it might be relevant for these terahertz cavities and things like that.
Thanks.
Yeah, so sorry, I had to attend to a couple of different things at the same time. So if you already addressed this, I apologize.
Okay.
But in the
Sure.
model that you were showing, and maybe this relates to what Jonathan was asking already, the model with the material in the cavity, the Hamiltonian that you had this sort of, I don't know, Pyers-like coupling between the light and matter operators, and that is quite different from, say, the usual ways, which is just a linear coupling, say A plus A dagger times, I don't know, your other operators, right?
What do you mean by the what do you mean by the usual?
I don't know, something like I don't know, James Cummings or something like that. You don't have the exponential of A dagger plus A.
Right.
You just have A dagger plus A.
I know what you mean. Yeah. So the James Cummings, the James Cummings is, of course, you have a dipole basically, right? And then you think about a dipole transition between a ground state and an excited state, and a dipole matrix element. In some sense, that's quoted in our theory as well. If you go to the multiband case, if you think about a two-band system, I was showing the slide matter coupling, right? If you think about a two-band system, then you have the dipole interaction, the dipole transition between one band and the other band, and this will have this linear kind of light matter coupling that you're thinking about. In the lattice model that we're looking at, this is the opposite limit. We start from basically the idea of minimal coupling of p squared free electrons, and then you have the J dot A term, the bilinear, and you have the A squared term, which is the diamagnetic coupling. This is well known, right? And now in a lattice, due to the nonlinearity of the band structure, you can get higher orders, and this is the Pyers substitution. So this is kind of an opposite. It's just a different limit depending on the material that you're looking at. But you're fully right. If I have two orbitals in a unit cell, then I also have this local transition, maybe by a dipole matrix element, or as I showed Christian's result of this interband Berry connection, when you think about the going beyond that limit, and then you also have this bilinear type coupling that you're asking about. So
maybe I forgot how you wrote this, but was this written in the K space or for the lattice, or was it already in real space?
It was in real space. Hold on, let me just share my talk once more. You're asking specifically, for example, this one, right?
Yes.
This is in real space.
Yes, that's right.
In K space, this would correspond to basically K minus A in the K dependent Hamiltonian, right? I should mention, of course, the Pyers substitution has limitations, right? It's known that it's only valid for long wavelengths and so forth. So as soon as you have intra-unit cell stuff going on and the field becomes strongly spatially inhomogeneous and so on, then we have to do something better than that. But this is of course all geared at long wavelengths, which is usually what you have in these optical or even terahertz cavities.
All right, thanks.
Go ahead, Jonathan.
Jonathan.
Yeah, thanks. Sorry for, I guess, monopolizing on So actually on the slide you just showed, maybe this is kind of related. Again, if I think classically about the photon field, then I would expect that the system you wrote down is kind of trivial because you can do a gauge transformation to completely remove the phase factor if it's spatially homogeneous. And I kind of expect a similar, like, even if it's quantized, I think like a homogeneous field should somehow decouple because you're coupling to the total center of mass momentum of the electrons, which should be a constant of motion. So was that with periodic boundary conditions, or because you also mentioned it was exactly solvable, so I feel like this must be related somehow.
Right. Yeah, that's a good point. Need to think about that aspect. Christian, do you have a good answer to that quickly?
Yes, I think you're actually right. So first of all, it's of course not true that that you can gauge away the vector potential now, because the vector potential will be something like expectation value of A plus A dagger, and this is time dependent, so you cannot gauge it away. And it's true that the electrons decouple from the photons because if the vector potential is spatially constant, then the Bloch waves are still the eigenstates, of course. Yeah, so in this sense, you're right.
Yeah, yeah.
Somehow the key to solving it exactly, because you know the electronic eigenstates already, which makes the problem much easier. If
right.
You know already the eigenstates. Yeah.
Yeah, I should have pointed this out a bit more. Yeah, that's a good point here. I noticed this only. I noted this only in passing. Right. You can write this as basically coupling the photons to the kinetic energy and the current of the electrons, and now these are both still commute with the Hamiltonian. Therefore, right, Christian? I mean, this is important that you have these. Basically, the electronic ground state is still the Fermi sea.
Exactly.
The photon wave function is changed by seeing the electronic wave function, and the excited states of the electrons are also changed. So in some sense, it's a bit pathological, you might say. You know, it's a mathematical curiosity. Exact solvability usually implies that, or in many cases implies that that the effects might not be so spectacular, or at least you could argue. But here, I mean, the interesting thing is that the electronic ground state is not changed, but the electronic excited states are changed, as you can see by the change in the spectral function and the development of these side peaks. So it's kind of a strange case. If anybody knows of other examples of situations where you have a coupled system and that leaves the ground state invariant but changes the excitation spectrum, then maybe I'm just ignorant. There might be other examples of that out there, but I think this is kind of an interesting case. But I should point out that this limit here, that this model here, in some sense, it's a generalization of a known exactly solvable model, which is in Mahan's book or in many other books, the Frank-Condon effect, like the single localized electron coupled to a bosonic mode. You can solve exactly, and you, for example, can calculate the spectral function and see that how the side peaks behave, and so on. And it's of course in some sense pathological limit, but it gives rise to a lot of insights that are known, for example, from the Frank-Condon effect, or polaron formation and sideband formation in shake-off states that are known also in electronic systems. Is that helpful?
Yeah, I think I see kind of what's going on. It's interesting.
Yeah, so you're right. I mean, and of course, the important part that makes this solvable is that we take this dipole approximation. So we take the momentum transfer to be zero. As soon as you relax that that part, then of course things become more complicated, because every momentum state of the electron couples to every other momentum state through the exchange of photons, and then the model is not solvable anymore. And the physics you might argue that the physics will also change, but we think that some of the features that you'd expect in this extreme limit would still survive even if you relax that constraint.
Okay, thanks.
Mm-hmm.
Are there any other questions?
Yeah, there was a question in the chat whether the general discussion that we're doing right now is going to be part of the recording, and I think yes, right?
Yeah.
All right.
Okay, well, good. Let me thank Michael again. I'll stop the recording now and